Okay, good morning. And we start, this is Math 5 lesson, yes? Okay, so we start this topic. This topic is very technical, yeah. I don't know how is your taste about mathematics. This is very abstract thing, but it's not hard because I'm following some logic here, and usually what we are doing in mathematics is based on rationality and logic. So this logic is probably already in your brain by evolution or something like that. So, but it is abstract. So we want to talk about the ideas of proofs, especially indirect proof and proof by contradiction, a little bit more. So let me just go. Uh, so what I will present probably will be somehow hard, okay? But don't worry about the exam things. It might be you will not get that much very questions from this topic in the exam, okay? But I want you to see, because there are very classic examples that it would be a pity if you just leave high school and don't see them, okay? So let me remind you about the statement. Do you remember in the very beginning of this lesson, we start talking about a statement. Do you remember what a statement is in mathematics? Sometimes people call it proposition, but let me just stick to the word statement. So a statement is a declarative sentence which is either true or false. Yes. So I don't want to go through that anymore, but let me just give you an example. For example, some books usually use capital letters to denote statements, like your book, but I prefer to use lowercase letter. I use less energy to write them, okay? So, for example, I would say that 5 is a prime number. This is a statement, yes? It is declaring something to you, and it is either true or false. In this case, it is a true statement, yeah? So that is true. I can have another statement Q. For example, I can write 7 is an even number. So this is also declaring something to you. It's a declarative sentence, but of course its value is clearly false. Yes, but that is the case. A declarative sentence which is either true or false, even if you cannot determine its truth value right away, it is for example, if I write a very big number and write that big number, for example, let me write 250, I don't know, 251 is a prime number. Okay, it is not that obvious to see immediately it is true or false, but it is clear that there are only two possibilities. Either it is a prime number or it is not. There is no other option. Okay, so that is a reminder of a statement. So if I want to draw a table for statements, a statement P has two possibilities, yes? Statement P, whatever P is either true or false. So this is the table of values, even though they are not values, but these are logical values, truth and falsity. So we say that any statement has two truth values possible for it, either true or false, okay? There's something called the negation of a statement, and you denote it by this symbol, and you read it as not P, okay? So this is not P. So for example, the negation of this, you read it like this. When I say what is the negation of P, you would say this is not the case that 5 is a prime number. Yes? Okay, but of course this is not a plain English. Yes, so how do you read it preferably in English? You don't say this is not the case that 5 is not a prime number. You say just
5 is not a prime number.
Yeah, 5 is not a prime number. So this is the negation of the statement P. And for example, what the negation of statement Q is in normal language, 7 is not an even number. We can also have an alternative here. So in principle, you should say this is not the case that 7 is an even number. In more proper language, you say 7 is not a prime number, not an even number. But in this case, we have also an alternative. What can we say?
7 is an odd number.
Odd number. Okay, so that is the way that you read negation of Q. But how do you think that truth value of P and not P are related? It's simple. If P itself is true, its negation is false. And if P itself is false, its negation is true. Yes? So that is the table of values that we have for P and not P. P is a statement. It has two possibilities, true or false. But not P becomes false if P is true, and it becomes true if P is false. Yes? So that's also the truth value for negation of P. Yeah, these are very simple things. These are not hard. Okay. There is one thing that we want to talk about here is a conditional. Or a conditional, if you want to, statement. A conditional statement is denoted, we need two statements, P and Q, and we say P, I put an arrow to the right and put Q, and I read it like this, if P then Q. This is the way that you read this symbol, okay? And this is called a conditional statement. If P, then Q, it's called a conditional statement. Now, what I want to do, I want to draw the table of the truth value for P and Q. Okay, sorry, for P, if P, then Q. I want to know when P, if P, then Q is true, and when it is false. Before doing that, let me ask you one question. What do you think? So let me tell you this. If Stockholm is the capital of Norway, then Oslo is the capital of Sweden. Well, how do you assess this statement? Do you think that I am saying something true or false? No, think about it carefully. Okay. So let me make if 2 is equal to 5, then 7 is equal to 9. How do you assess this statement? Okay, this is a very strange statement, but what is your feeling here? Do you think at the end of the day, this statement is true or false?
False.
Your feeling is it's false? Okay, yes?
It's true because the first one doesn't occur, so we can say it.
Yeah, so I think that is the correct way of thinking. I don't know, there is no way that I can tell you that this is the logic, because it is something like that, okay? So let us say that we are humans, we argue with each other, okay? And then from my point of view, you are saying something nonsense. I would say that, okay, well, how is that happen? You say nonsense, it's nothing, but when I say nonsense, you become sensitive. It's exactly like this, okay? If you say 2 is 5, okay, then I tell 7 is 9. And you cannot complain, can you? Is that understandable? I just want you to see, because you see, I am telling 7 is equal to 9, okay? You start complaining, well, but how is that possible 7 is equal to 9? I would say that from the place that you say 2 is 5. If you say 2 is 5, then I am also allowed to say 7 is 9. Yes? You cannot go against me because of this argument. Because if you say, no, 7 is not 5, I would say that, okay, 7 is not 5, but how is that possible 2 is 5? But if you insist 2 is 5, I can also say 7 is 9. I'm just giving you the feeling, okay? I'm not saying this, yes.
So if you give me 2 equals 5, I can give you whatever numbers.
Yeah, exactly.
And it will be true.
True. Because if you're, sorry for that, but if you want to say nonsense, I'm also allowed to say nonsense, yes? You cannot complain. You cannot yourself say nonsense, and when it comes to me, you say, well, you're not allowed to say nonsense. Yes? I mean, this is rational. It's a rational thing, yes. Okay, so we want to understand these things a little bit better. So if I have two statements, P and Q, so here, 2 is equal to 5. By the way, this is a statement, yes, because it declares something. 2 is equal to 5. which is of course a false statement. Okay, so if I call this P and then I call this Q, this becomes if P then Q. So I can write it as if P then Q. Yes, something like that. Okay, so now if I have P and Q, I have how many options for the truth or falsity of F2? Either true or false. I have 2 options for Q, either true or false. But if I want to consider both of them simultaneously, how many possibilities I have? 4. Yes? Because this might be true, this might also be true, this might be false, this might also be false, or this might be true, this false, this might be false, this be true. These are the only 4 options that I have for 2 statements, yes? Is that understandable? Okay. Now, I want to see what is the truth value to this conditional statement. And I will try to give you a feeling so that you can, so let me say P, you get an A, you get an A. Q, I buy you an ice cream. Ice cream. Yes? So if P then Q, if you get an A, I will buy you an ice cream. Okay? Is that clear? So let us say this is our agreement. Under what circumstance or circumstances you are annoyed? When what happens, you feel something against what we have the agreement for. Yes, Melvin.
If I got an A and you don't buy me an ice cream, then the statement isn't true.
You feel that how human this Babak is. Yes, I got an A, but he didn't bother to buy me an ice cream. And I want this is clear. Everyone agrees with that. Yes, in this circumstance, you say that okay, this is not according to our agreement because I got an A, but you are not standing in your words. Okay, so is this the only possibility that you are annoyed? Be careful about answering. There is no way that I can teach you these things. I'm just trying to see what is your feeling. Yes? Yes?
I think you will be annoyed if you buy me an ice cream and I don't get A.
But this is not a course. Yes. If I will, then I will be annoyed. I am not talking about me being annoyed. This is a good point. I am talking about when you are annoyed. Yes? I'm not saying someone gets annoyed. That's actually a very good thing that you told me. The point is that when you feel bad, yes?
When you don't get an A and you still would hold your word and buy me an ice cream?
No, because in that case you are a very good person. No one will complain about that, yes? No, I just want to see the phrase. There is only one possibility. If you feel bad about this because you are so conscientious, you say that I don't deserve to have an ice cream. No, this is not in logic, okay? So, yeah. Okay, so there is only one possibility that you get pissed off from me, and that is when you do what you're supposed to do, but now I don't stand for it. So it means that of all these possibilities, only this one is false. When you get an A, I don't buy an ice cream, you feel something wrong. So that is F. But in other cases, students usually don't have problems for understanding this. If you get an A, I buy you an ice cream, everything is okay, so it's true. This one you felt it is not true. What about the last one? It's also true, you don't complain, yes? You didn't get an A, and I also didn't you buy an ice cream. Nothing happened. You don't feel bad, yes? So that's also true. That's exactly this scenario. Yes? And then what about this one? This sometimes a student get confused. You see, you don't get an A, I buy you an ice cream. Did I violate the agreement?
Yes.
And then I don't know how to say it. Think about it. Did I violate our agreement? Or I made a new agreement? Or I did something which is not in contradiction what we had before? Because I told you, if you get an A, I buy you an ice cream. You haven't got an A and still I bought you an ice cream. Did I violated the previous rule? Yes?
No, because it would only violate it if you only did Q if and only if P is true.
No, if and only if is a very serious thing. Don't say if and only if. If and only if means double arrow, double-sided arrow. Okay? No, I didn't say if and only if. If and only if you are right. I would say that I would buy ice cream for you if and only if you get an A.
Then it will be a violation. But in
Yes,
this case,
yes.
it's not
If that is your, yes, you understand what I mean. So that is also T. Okay? If this way of understanding is hard, I think the first way is not hard. I ask you under what circumstances you feel annoyed, and that is only one circumstance. You get an A, I don't buy you an ice cream. Simple as that. Okay? So that is the statement true. There is a name for the first one. P is called the premise. And this one is called the conclusion. Okay? So, if I want to summarize this table, I would say, it is important by the way, the one on the left before the arrow is called the premise. The premise means the hypothesis or the assumption, and Q is the conclusion. Okay? So if I want to summarize the data in this table, I would say that the conditional statement P, a conditional statement is false only if the premise is true and the conclusion is false. Yes, because the other cases is TTT. Yes? So let us emphasize on this sentence. A conditional, whatever the names are, a conditional statement is false if and only if the first one, which is the premise, is true, but the second one, which is called the conclusion, is false. And that is reasonable, yes? If I give you the correct information and you are getting something wrong, and that is exactly why we have the exam, because I provide the correct information, you give me the wrong answers, you get points, and you are not pissed off because nothing has happened, yes? Yes. Questions? Okay. Now, one thing that I want to talk about, we have two terminologies when it comes to a conditional. One terminology is called the converse, and one terminology is called the contrapositive. Okay, the contrapositive. The converse, the idea is simple. You just swap the premise and the conclusion. So it becomes Q, then P. This is the converse of this. It's just the definition. Yes? For example, if I switch that, I buy you, so here is, I buy you an ice cream. If I buy you an ice cream, then you get an A. Do you see that this is a different story from the previous one? Somehow here I am threatening you. Yes, I buy you an ice cream and you will get an A. You feel the difference. It's not equivalent to the same thing we had before. Yes? Yeah. Anyway, so this means that this is logic, because I'm not teaching logic to you. Logic is what we are constructing math on top of it. But contrapositive means not only you swap them, but you also negate them. Yes? What is the meaning of this one? If I want to read this is not the case that I buy you an ice cream. If this is not the case that I didn't buy you an ice cream, then you didn't get an A. And now what do you feel about this new sentence? Our agreement was, if you get an A, I will buy you an ice cream. When I just simply swapped them and read the statement for you, you felt that this is not the same. Okay, we will check it out. And now I am saying that not only you swap them, but you negate both of them. And let us read this again. Of course, I have to adapt the grammar in English, yes? So I would say that this is not the case that I bought you an ice cream. So, sorry, if I didn't get you an ice cream, then you didn't get an A. Why? Because our agreement was that if you get an A, I will buy you an ice cream. When you see that I haven't bought you an ice cream, it means that you didn't get an A. Okay? So this one is, I hope that you understand, is the same agreement expressed in a different language. You need to take your time to understand it a little bit yourself. Is that understandable? Because from a mathematics point of view, I can easily prove it for you, that these two statements are the same. I will show it right now. But first, before doing that, I want you to feel it yourself, yes? Do you agree that's the same agreement? Yes? If I didn't buy you an ice cream, then you didn't get an A. That is the same thing. Because why? Because I were supposed to buy you an ice cream if you get an A. If you see that I haven't got you an ice cream, if I still stand on my agreement, it means that you didn't get an A. Otherwise, I would have bought you. So that's the same statement. Okay? But let us try to understand it from a little bit more abstract mathematical way of doing it. So if you don't mind, let me continue this table. Can you tell me what is the table of values for the converse, QP? Do you remember? I told you this part in words. The information I learned from this part of the table was a conditional is false if and only if the premise is true and the conclusion is false. If I write it the other way around, this will be the premise and that will be the conclusion. Okay, so now can you tell me how should I fill it up with T or F? So this line, P and Q are both true, but remember, Q is coming first, P is coming second. So T, then T is T. Here, F comes first, be careful, and T comes second. The answer is T again. But here, T comes first, F comes second. The answer is F. And then here, FF is again T. Yes? And now compare these two columns. This column is TFTT. This column is TTFF. They coincide on this line. They coincide on this line. But they don't coincide on these two lines. So they are not equivalent. And that is what you felt. The sound of threatening you, yes? That is when I stood, you realize that's not the same thing. But I want to continue this table, so if you don't mind, I want to take this one and put it in my table, okay? So what do I need to put in my table? What do I need to put in my table? Because I want to construct not Q, then not P, I need a column of not Q, I need a column of not P. I also need a column of not Q, then not P. Okay? So how can I fill up the column of not Q? I look at the column of Q. Not Q is the negation of Q. So what happens? If this is T, it becomes false. If this is false, it becomes true. If this is true, it becomes false. And when it is false, it becomes true. Yes? And now what about this one? This is the negation of the first column. So TT becomes FF, and FF becomes TT. Yes? And now can you tell me what should I write here? Be careful. What is the name of the premise here? The name of the premise is not Q. The name of the conclusion is not P. So the premise is false. The conclusion is false. The conditional becomes true. Yes? Now, the premise is true, the conclusion is false, the whole statement becomes false. The premise is false, the conclusion true, so it is true. True and true, it's also true. Now, compare this column, which is the values for this conditional, and this column, which are the values for this conditional. They are identical. Yes? So if you don't like, that is good. You know, this is logic, so there is no proof behind that. But using mathematics makes it more clear what we are talking about. So definitely, this guarantees you that this conditional, and its contrapositive are actually equivalent. Okay? Yes. Okay, this is expressed in the book without discussing about why or how, okay? So if you don't like about how or why, you can forget about it, but you need to know this relation. So if I have P, then Q, this is equivalent. So equivalent in mathematics is written by double arrow to its contrapositive. So this I want you to know. Okay. So here, if you want to prove this is true, this, if you start from here and do a step by step and reach to here, this is called a direct proof. Okay, which we always do. But sometimes proving this statement is hard. I will give you an example. Then instead of proving this one, you rewrite your problem in the new language and prove the truth of this one. Because these two statements are more or less mathematically the same, so it means that if you prove this is true indirectly, you have shown this is also true. Is that clear? That is called an indirect proof. So here I will give you an example that we can solve it both with direct proof and indirect proof so that you understand what is what. And then I will tell you that this is not always the case. Sometimes we cannot use the direct proof, not because the problem statement is hard. I will give you examples. So let us not confuse. Okay, this is the first example. So let x be a real number if, show that, or prove that, doesn't matter, show that if, a very simple example, for 2x plus 4 is greater than 8, then x is greater than 2. Okay? So these type of questions are probably the questions that you will get in an exam to understand what is going on. It's very, very simple. Okay, I am telling you that if this is the case, show that x is greater than 2. Yes? I will solve it in two different ways so that you can compare the methods. Method 1, the direct proof. Okay, so when I say, first of all, if I say the direct proof, if this is my statement P, then this is my statement Q. Yes? So this can be written P, then Q, using the arrow. Yes? P, then Q. Direct proof means start with your premise, start with your assumption, and do mathematical, logical things, and reach to your conclusion. Okay, so let us just do that. It's extremely simple. It's a Math 1C problem, yes? So what do? You say that 2x plus 4 is greater than 8. If this number is greater than that number, so this number plus negative 4 is also greater than that number plus negative 4. Understandable? If you say this number is greater than that one, then you have to accept that minus 4 added to it becomes bigger than if minus 4 is added to this. Yes? But then what happens? Minus 4 and 4 are cancelled, so 2x is greater than this becomes 4. Yes? And then I divide everything by 2, x greater than 2, end of the story. So this is, you see, I have started with P. This is my P. I continued and I reached to Q. So this is the direct proof. Yes? But, which was very simple. And now I want, just for your understanding, because if I ask you to do that, then of course when you write this is correct. Okay, but the method number 2, I want you to understand this method. Method number 2 in direct proof. So what is the meaning? The first thing, let us understand how should I write the contrapositive, yes? Because P was that expression, 2x plus 4 greater than 8. This is my P. If P, then Q is x greater than 2, this is my Q, yes? Now, can you write the contrapositive? The contrapositive is negation of x greater than 2, then negation of 2x plus 4 greater than 8, yes? Can you write a better way? Because when you say x greater than 2, negation means this is not the case that x is greater than 2. Then what happens? Yeah.
2 is greater than x.
No. Be careful. Yes?
X is less than or equal to 2.
Less than or equal. You didn't say that one. When you say x is not greater than 2, there are two possibilities. Either x is equal to 2 or less than 2. So a better way of writing this is simply writing this. Yes? Then, again, what is the negation of this? This is not the case that 2x plus 4 is greater than 8. In a better language means
2x plus 4 is
less than or equal to 8. Yes? So, if you prove this, you have proven the contrapositive, but the contrapositive is equivalent to the original statement, then you are done. But if you do it in a very odd way like this, that is called proof, indirect proof. Okay? So, instead of proving this gives me that, I only need to prove this gives me that. Is that clear? So, because the rest of it is very simple. If you have questions, please let me know right here. I am not forcing you to use method 2, because in this case, method 1 was very easy. So why should I bother to do that? But this is a good example to see how they are actually done in practice. Do you have any other question here? If I want to prove this, I need to prove this. The first thing that you do, you write the contrapositive. The contrapositive is this one, and then you prove this one. Okay, but that is easy, because now I start with my premise. The new premise is this one, and I want to reach to this conclusion. Again, what do I do, for example? I multiply everything by 2, and then I add 4 to both sides. Then it becomes 2x plus 4 is less than or equal to 8. Okay? The only thing that I want you to understand is not the algebra. The algebra in both cases are extremely simple. But I want you to understand that if you show the truth of this, it means that you were able to show the truth of that. They are equivalent. Yes? Is that clear? Okay. But now let me give you some examples that direct method usually doesn't work. Don't think that these are hard problems. These are extremely simple problems. Let us see how it works. Okay, so let me start writing some problems on the board. We start with this one. Example, very simple. Let n be an integer. Show that if n squared is even, then n is even. Yes? This is a very simple and typical example when it comes to this concept, because it's very easy to understand, but this is, you see that it is not possible to do it using it is possible, but it becomes extremely harder. But the proof by indirect proof makes it very easy. First of all, let us see that we understand the problem. The problem tells you that if n is an integer and someone gives you n squared, and you see, I imagine an n in my head. I don't give you the n, I give you the n squared. and you look at my n squared and you see that my n squared is even, my goal is to show that the number that I thought has to be even as well. This is not the simple one, because some people get confused. Some people say that, okay, I don't know, 4 is even, so 4 to power 2 is 16, 16 is also even. Don't think in that way. That's the other way around. That is the converse. The converse is simple to prove. Yes. So do you see that n squared is even is my p, n is even is my q. If p, then q. Okay. What is the converse? The converse tells you that. Can you read the converse for me? So let us consider this to be p. Then let us consider this to be q. If p, then q. Read the converse. The converse is what?
If Q then P,
If q, then p, which means in language means if
and is
n is even, then what?
n squared.
N squared is even. Okay? This might be true or false. We have to check it out, but this is different from there. Yes? I want you to understand. This is very simple to prove. Why is that? Because when you grant me that n is even, I am allowed to consider n as 2 times q. Okay? Q is an integer. Do you agree? When you say me n is even, then I am allowed to write this. But now, what happens for n squared? N squared becomes 4q squared. Yes? But 4q squared can also be written as 2 times 2q squared. 2q squared is an integer, so I can call it capital Q, so it becomes 2 times q. So if you grant me that n is a multiple of 2, meaning that n is even, by doing this very simple algebra, I realize n squared is a multiple of 2 as well, so it means n squared is also even. So the proof of this one is easy. But I want to, because I have seen these mistakes, if I give you that in the exam, if you write this, even though you have written everything correctly, but that is the proof, not of that, but for this. Do you understand the difference? This is Q then P, but I want to prove P then Q. Okay, now you might think that, okay, let us use the same method. Okay, that is a direct proof, yes? Because I started from my premise and I reached to my conclusion. This was a direct proof for this. You might think that, okay, let us do the direct proof here as well. Let us see why you fail, so that you can feel you need proof by indirect proof. Okay? So let us see, I want to do the same idea as before. But what is my assumption now? My assumption is that n squared is even. Yes? Okay? I will do the same thing. You will tell me that, okay, n squared is even. You are granting this. Then I am allowed to conclude that n squared is 2 times an integer. Do you agree? Where q belongs to z. So far, so good. This is not wrong at all. You tell me this is true. I am allowed to conclude this. But then when I look, I want to know something about n. Okay? Here, you told me something about n. I wanted to know something about n squared. It motivated me to square both sides. Here, you are telling me something about n squared. I am supposed to get something for n. So it motivates you to do what? Take square root. Okay? So you take a square root. Let us say it is possible. And it becomes n. And on the right-hand side, of course, you have plus or minus. Let us assume that n is a natural number. I don't want to disturb you with these things. I will get this one. I will get that one. Okay? But the problem is that, can you see that I cannot conclude that n is even because I see this? Do you understand me? Because n is equal to a square root of 2 multiplied by square root of q. So I cannot say every number written in this form is even. I can say that a number which is a multiple of 2, an integer multiple of 2 is even. This doesn't mean that this equation is wrong, but it is not helpful to conclude that n is even. Yes, do you understand what I'm saying? Okay, so if you stop here, you haven't still proven this yet. But the problem is that you even didn't disprove it yet. So you are in a limbo situation. You are between the earth and the sky, okay? You didn't prove it because it is not possible to conclude that n is even because of this form. And you didn't disprove it. So you did nothing. Yes? Is that clear? Okay. So this is why I am saying that I want you to feel that. Even though this one is the converse, but the direct proof was applicable to the converse immediately. But I wanted to take the same strategy of direct proof. For this one, it failed. Okay? Okay, this is that I want you to understand. So this is important to understand that why we need a new method of proof. Because sometimes it doesn't work. Okay? But now, let me clean this. Now, instead of proving the conditional, I learned that I can prove the contrapositive of the conditional. So read the contrapositive of the conditional for me. So P, then Q. The contrapositive is not Q, then not P. Yes? Now read it for me. So how can I read this? This is not the case. So this is not, what is Q? N is even. Then not P. N squared is even. Do you agree? So I realized that the direct proof didn't work. I think about indirect proof now. The first step is to write the contrapositive appropriately. This is the first step in writing the contrapositive. And now try to read it in plain English. This is not the case that n is even, means n is not even. Yes? Then, what do you say here? N squared is not even. In this special case, you can even write better. Yes? Now, this is not always possible, but we have a word in English for it. For not even, we have a better word. It is odd. So n is odd. Then n squared is odd. I want you to understand, if you show this is true, you have shown the original statement is also true because they are equivalent. Okay? But now you see that it is a miracle happening because I couldn't do the direct proof for here, but I can do the direct proof for the contrapositive one. Okay? So you can momentarily forget about your original problem and concentrate on this one. So now what I am granting you, in the original problem, I am granting you n squared is even, but in the contrapositive version, what I'm granting you, n is odd. Okay? Now, when you say n is odd, everyone who knows mathematics can write there exists. So if you, let me write it like this. N becomes 2 times q plus 1. When you say n is odd, it means that n can be written in that way. Is that understandable? Okay. But now what do I want to say? I want to say something about n squared in the new version. So it motivates you to square it. So you see the same solution will be more or less available now. So now I square it. It becomes 2q plus 1 to the power of 2. And this is a simple algebra. So n squared becomes 4. The first one is squared 2 times the first one times the second one plus the second one. Okay? And I factor a 2 out. Even though I can factor more, I don't need it. I just factor a 2 out. So it becomes 2q squared plus 2q and then plus 1. Is this an integer? Yes, because q was an integer, so this combination is an integer, so I can call it the capital Q. So then it becomes 2 capital Q plus 1, and capital Q is in Z. So now look, what do I have in my hand? N squared, that I was looking to know something about it, is 2 times an integer plus 1. What does it mean? It means n squared is odd. So therefore, n squared is odd. So let me write here, therefore, n squared is odd. Okay? Is that understandable? So I want you to feel that you didn't prove something else. You proved the same thing in a different language. Okay? And this is not that thing. Is that clear? So that is the meaning of indirect proof. So you saw that in this problem. Your motivation is usually always to do the direct proof, but sometimes the direct proof doesn't work for this reason that I just told you. Okay? Is that clear? Okay. but the way that I write this, if you decide to do something, so let me write it again. Okay, I want you to understand what we are doing. But if that is given in the exam, I myself prefer to write it. Mathematicians also write it like this. So I would say that n squared is even. I want to prove that n is even. Okay? This is the way that I think. If you agree with me, n is even, fight is over. If you disagree, it means that you have to tell me that n is odd. Okay, so I would write like this. This is the better way. You don't need to elaborate all these things. So you write that, okay, we prove that, we want to prove that, something like that. You want to prove that n is even. Assume that this is not the case. Yes, you see, this is a very common phrase in math texts. Assume that this is not the case. If this is not the case and n is odd. Okay? Instead of writing so many things, this is the way mathematicians write the text. We want to prove that n is even. Assume that this is not the case. What does it mean? It means n is odd. Then write everything. Therefore, I don't want to write it. So 2q plus 1, q in z. You continue everything I wrote there. Therefore, so hence, n squared is odd. Yes? Then, but this contradicts the assumption of n squared being even. Yes? So you see, this is the structure. I want to prove that n is even. If you agree with me, fight is over, we go home. If you disagree, it means, assume that this is not the case, then you have to admit that n is odd, and then live with the consequences. Yes? So you start living with the consequences, and you got that n squared is odd. But this contradicts the assumption you gave me that n squared is even. So it means that if you agree with me that n is even, we are friends. If you disagree with me, then you have to contradict yourself, because you just told me n squared is even, and then you have to admit that simultaneously n squared is odd. This cannot happen. This contradicts your own assumption. Yes, is the logic clear? Yes or no?
Yes.
Okay. So this example I want you to know. Then I want to solve two hard examples. I am not solving them. I am just presenting one else's proof to you. But these are classic examples to see how proof by contradiction or indirect proof are actually powerful. One of them, I really enjoy it whenever I do it myself. It goes back 400 BC by Euclid. Okay, so Euclid wanted to know how many prime numbers are there. So you probably know the answer. How many prime numbers are there? Infinitely many. But it is not that obvious. When I was at your age, it was very surprising to me, because I was thinking in this way. Okay, apparently this is not correct. I was thinking that, okay, when I go further and further, and if the number becomes very big number, okay, the chance of this number being divisible at least by one of the previous number grows. Yes, if I write a very big number here, you have a lot of numbers before that. Okay, I was thinking, I'm not saying apparently this is wrong because this is not working. Okay, I was thinking, okay, at some point, from some point onward, might be there are no prime numbers at all, because at least that I can find one single number which that huge number is divisible by. So it was not that trivial that there are infinitely many prime numbers, especially for 400 BC. Okay? Is it 400 BC Euclid? I don't remember. Anyway, either 400 BC or 400 AC, but still it's quite long from us. Okay, so the proof, this is a very elegant proof. I don't expect you to come up with the idea yourself, but I expect you to see the simple statement of Euclid to prove that there are infinitely many prime numbers. You will probably enjoy it if you like mathematics, of course. Okay, so the idea of the proof is this. Euclid is telling you that there are infinitely many primes there. Okay? If you agree with Euclid, we are done. No fight. Exactly like this. If you disagree, what does it mean? Okay? So I want to prove that. We prove that there are infinitely many prime numbers. Okay? We prove that there are infinitely many prime numbers. Assume that this is not the case. And the case, and I don't know, if this is not the case means what? There are finitely many. And if you have a finitely many, you can write the list. Okay? So assume that this is not the case and p number 1, p number 2, p number 3, up to some p, I don't know, p number say n, is the only prime numbers, are the only prime numbers. Yes, do you see the logic? We want to prove that there are infinitely many. If you agree with me, we are done. If you don't agree with me, then you mean there are finitely many. So let me write the list of all prime numbers that you agree there are there in the universe. I wrote them down. Imagine. Okay? Now, this is very creative from his side. He constructed a very peculiar number. Okay? He said that, okay, let n be the following number. And this is his creativity, actually. P1 multiplied by P2 multiplied by P3 multiplied by Pn, and then plus 1. I don't know how he came up with this number, but whatever it is, yes? So, if the prime numbers are finite, I have a list of them. I take that list, I multiply the numbers in that list, whatever that number is, I add 1 unit to it. 1 unit to it. Okay, so that becomes a new number. First of all, tell me, do you agree with me this number is definitely greater than 1? Yes, because the list of prime numbers, the smallest one is 2, let alone the other ones. So if you multiply them and add 1 to it, definitely it becomes a number greater than 1. And if a number is greater than 1, you know that you can factorize it. Yes, so if a number is greater than 1, do you remember this method? You write the prime numbers here, and then finally you came up with number 1. Yes? So you can factorize it. Okay, so since n is greater than 1, n has a prime factor, q. Yes? Do you agree? Because if n is greater than 1, n has a prime factor q. Do you agree? Okay, but now do you also agree? So let me underline this prime. So when you say that this is a prime factor for n, what does it mean? It means n is divisible by q. So let me write extra piece of information so you are not confused. When I say q is a factor of n, it appears somewhere in this list when I factorize it. So n is divisible by what? Q. When you say is a factor of n, it means n is divisible by q. Yes?
Is q all of the previous prime numbers?
That's the point. That's the point. We know that Q is a prime. Yes? This is we know. On the other hand, you told me this is the list of all primes. So what does it mean? It means this Q has to be one of them. Is that right? Because we want to prove that this is infinite. If not, I tell you, okay, you say me this is not infinite, so write please the list of all of them. Okay? You write the list of all of them. And he constructed a very peculiar number here. And then he said that this number has a prime factor, call it Q. On the one hand, it has a prime factor. On the other hand, you told me this is the list of all prime numbers. So what happens? This Q is one of these numbers. Is that clear? Yes. So, okay. So, since n has a prime factor, on the other hand, since since P1 up to Pn is the list of all prime numbers, Q has to be one of them. Is that understandable or not? Yes? If Q is one of them, then P1, P2 up to Pn, therefore, thus, this is divisible by Q as well. Do you agree this part? You see, this is the list of all prime numbers. Imagine this is the list of all of them. We know that we cannot write all of them, but let us assume that we can. Okay? And then I would say that n is a number greater than 1, so I can factorize it, and then you see a lot of prime numbers. I don't know, you see some prime numbers here. Pick one of them and call it Q. Okay? And Q is a factor of n, so n is divisible by Q. On the other hand, you just assume that this is the list of all prime numbers. And because Q is a prime number, it has to be in this list. Yes? So Q is one of them. If Q is one of them, do you agree that this number is also divisible by Q? Yes or no? Because Q is among them. Yes? So this one is divisible by Q. Okay. N is divisible by Q. This is divisible by Q. Yes? This one is also divisible by Q. Yes? So the difference of them should be divisible by Q. Do you agree? If two numbers are divisible by the same number, the difference should be divisible by the same number. Yes? We had this before. Okay, but what is the difference between these two numbers?
1.
1. So we have to agree that 1 is divisible by Q. But Q is prime. So it starts from 2 at least. So how is that possible? That 1 is divisible by a number bigger than 2. It's not possible. This contradiction, if you want to live with this contradiction, you have to agree that there are finitely many. Because as soon as you agree that there are finitely many, then you come up with this contradiction that a number 1 is divisible by a number greater than 2. Greater than or equal to 2. Is that clear? So that's a contradiction. So this means that there are infinitely many prime numbers. Is that understandable? Don't worry about if you know, but this is very simple and elegant. Okay? Because if I didn't, I don't know how much time we have, but if I wanted to ask you what is your opinion, by the way, why this shows there are infinitely many? I didn't tell you that yet. Why this argument shows you that there are infinitely many? Yes?
It disproves that there are limits. There's a limit of time.
Yes. Yeah, something like that. Because when I assume that there are a finite list, then it means that I have to live with it that 1 is divisible by a prime number. If you tell me what q is, I don't know, but I know q is a prime number, and I know that 1 should be divisible by that prime number, which is contradiction. So when you assume that there are finitely many of them, then you are in trouble. Yes or no? Okay, this is a very classic example of proof by contradiction. I even don't know even how, if you want to see the proof directly, I hope that you understand, proving it directly is very hard. If you want to show that a set contains infinitely many numbers, how do you want to prove it directly? You see, I want you to feel, that's why mathematicians have designed this, have developed these methods of indirect proof, or proof by contradiction. Okay? Okay, so is that clear? There is one classic example which is also in the exercises in the book. These are too much for exercises, okay? So let me just do it for you here. The other very classic example is this. A square root of 2 is irrational, okay? Square root of 2 is irrational. First of all, what is the meaning of irrational and what is the meaning of rational? Yes?
Rational number can be expressed as the integer, as the ratio between two
Integers. For example, 1.5 is a rational number. Why? Because I can write it as the ratio of two integers. Okay, of course, this is not a unique name. I can simplify it with 5, it becomes 3 over 2. Anyway, because I was able to write it as a ratio of integers, this is important, I say that 1.5 is rational. Okay? But I want to say square root of 2 is not rational. What does it mean? It means that I need to prove you don't look for integers so that when you divide them, it becomes square root of 2. By the nature, they are very hard. They are very big claims. Because how many integers in the world we have? I have infinitely many. I am telling you, don't look. You will never ever find a pair of integers so that when you divide them, it becomes exactly square root of 2. Okay? This is not possible. Yes? That is why when you take a square root of 2 and put it in the calculator, you get a lot of decimal points. No matter how big you have for your display, it will never end. So the decimal points will continue forever without ending. That is the meaning of being irrational from another perspective. Okay? So we want to prove that the square root of 2 is irrational. It means that it is not possible to write it as a fraction of integers. We want to prove this. Okay? So how can I prove that? I used proof by contradiction, or I would say that, okay, if you agree with me, this is irrational, fight is over. If you disagree with me, then you have to agree that I can write it as a fraction. Okay? So I would say that assume this is not the case. And square root of 2 is rational. Is not irrational means it is rational. Yes? So when you say a square root, when you admit that the square root of 2 is rational, you have to admit that the square root of 2 can be written as m over n. What are m and n? M and n are integers. I want to add something else. I want to add GCD of m and n is 1. Okay, so let us understand this. If you don't agree with me that a square root of 2 is irrational, you have to agree that it is rational. When you agree it is rational, you have to agree that you can write it as a ratio of integers. And by the way, I don't need to write integers, I can write natural numbers because the square root of 2 is obviously positive. Okay? But this is a little bit problematic for a student sometimes. I am saying that GCD of m and n is also 1. It means that m and n cannot be simplified. You see, in this case, this was correct. This was also correct. But from now on, I cannot simplify any further. Okay? So if it is not possible to simplify, okay. It means this condition is automatically fulfilled. If I can simplify, I simplify until that place that I cannot simplify any further and call this one m and this one n. Okay, so this is always possible, but this is very crucial. Okay, so if you say that a square root of 2 is rational, so it means that you can write it as a fraction of natural numbers so that this cannot be simplified further. Yes? Okay, now everything is a very simple algebra now. Yes? I multiply everything by n and I square it. Yes? And then I write a sentence. Do you agree with me? I'm just coming in this direction. 2n squared is m squared. Do you agree that I can conclude m squared is even? Why? Because m squared is a multiple of 2. But now look at the first problem on the board. If a square of a number is even, what can I say about the number itself? It's also even. So I go one step further. M is even. So already this is proof by contradiction within proof by contradiction, because this step was proof by contradiction. Yes? So m squared is even. If a square of a number is even, the number itself is even. So m squared is even, so m is even. Yes? But what is the meaning of m is even? When you say m is even, it means that it is a multiple of 2. K is an integer, yes? So every step is legal, yes? But when m is 2k, I put it back in this equation. Okay, so what happens? It becomes 2n squared is equal to 2k to the power of 2. And then it becomes 2n squared is equal to 4k squared. I just raise it to power 2. I simplify. N squared becomes 2k squared. Do you agree with me if I write n squared is even?
No.
N squared is 2 times k squared. So it is even. Yeah, if you want to disagree at that level, then I don't know what to do, okay? So n is even again. Why? Because of that problem again. N squared is even, n is even. Yes? And now we are in contradiction. Why? Yes?
Because now the greatest common divisor is at least 2.
2. Yes? Because m is even, we realize that m should be even. We also realize that n is even. If I have 2 even numbers and I write them as a fraction, can I still simplify them? At least by dividing by 2. But I assume that I am not able to simplify them. So I have to have both scenarios. I have to be able to simplify and cannot be simplified. Yes? So this cannot happen. So this means that a square root of 2 cannot be written as a fraction. Because if a square root of 2 can be written as a fraction, this fraction either is in its simplified version, or you simplify it as much as you can. At some point you cannot simplify further. The numerator you call it m, the denominator you call it n. So the m and n that I have written here is no longer reducible to smaller fractions. Okay? This is on the one hand. M and n are not reducible anymore. But if I follow this logic, it tells me that m is even, n is also even. It means simultaneously m over n is reducible. On the one hand, m and n is not, m over n is not reducible. On the other hand, it is reducible. So it cannot be simultaneously reducible and not reducible. This contradiction comes from the fact that I am assuming that this is rational. So these two classic examples are hard examples. You don't need to be worried about this level. I don't know, for some reason they wrote it in the exercises, but might be they have provided a lot of hints. I don't remember. Okay, but this is in the body of the text. So this lesson shouldn't disturb you. Okay, so you don't be worried. This is a very technical lesson. But I wanted you to see that even with the mathematics at the level of high school, you could do a lot of things. Okay, but proving irrationality is extremely hard. For example, you have to wait for the university if you're interested to know why pi is irrational. So pi is the famous pi number, okay? And then even harder than that, I think proof of pi is harder. And E is also the Euler number that you studied in Math 3C. So these are very famous irrational numbers. Only this one was at the level of high school and we could do it like this. Okay. Any questions? No? Okay, so Yeah, I mean, the only thing that I want you to take on is to understand the method of proof by contradiction and indirect proof conceptually, and feel that you really sometimes need them. Not because of these very elegant proofs, but because even for this very simple problem, which is exactly is at the level of your lesson. So even for this very simple problem, you cannot prove it directly. You have to prove it, for example, by indirect proof.
I just want to describe a rational number as a number that has infinitely many decimals.
This is a consequence of the definition. Yes, but you can view it like that.
But then 10 over 3 wouldn't be irrational.
No, that is rational. So no, what you said?
10 over 3.
No. The first question.
My question was, is a rational number a number that has infinitely many decimals?
No, every number. No. No, that's the only thing. That's the only definition is that you cannot write it as so. But for example, as you said, 0.03333, etc. This is not irrational because this is 1 over 3. Okay, no, but irrational means that. But there are some. So if you want to know the theory, is that if there is a pattern for it and it repeats the pattern, then still it is rational. So for example, you can have this one, 0.1, 2, and then 3, 5, 7, 3, 5, 7, 3, 5, 7, and this goes forever. This is also rational. We can prove that this is rational, okay? But if the pattern, you don't see any regular pattern, then it is irrational. For example, 0.1, 0, 1, 2 zeros, 1, 3 zeros, 1. You see a pattern, by the way, but the pattern should repeat itself. But this pattern is not repeating itself. And even though you have a pattern, but the pattern is not repeating itself. So this is irrational. But the definition, this is hard to show that this is irrational, okay? So proving that numbers are irrational, it's not that easy in usual, okay? But if you have a repeated pattern going on, then that number, even though it might have infinitely many decimals, that is still rational. And the example that you said is the best example. 1 over 3 is continuous forever. Yes? But this pattern 3 is repeating itself over and over again. Okay, any questions? No? So I think we stop here. Thank you.